Welcome back to our study of differentiation. And today's topic, we're going to be talking about implicit differentiation. We'll get a pen here. First of all, maybe we talk about what does the word implicit mean. Implicit is like an implied, it's not, and maybe the best way to define it in this context is to show what's an explicit function of x. So that's what we've been working with recently. Explicit, where we say y is a function of x, and you might have, let's see, a favorite function here, x squared plus the sine of x. You give me an x, I'll give you a y, and we've learned to take derivatives of that. We'd say, well, what's the derivative? The derivative of this is what? It's 2x plus the cosine of x. And what did this give you? This gave me the slope of the tangent line of that curve. And I'm going to, I don't know, I do kind of a tough one here to figure out, but let's say there's a little wiggle on I'm kind of a little bit of a guess what that might look like. And this derivative then gives me what? It gives me the slope. Again, this derivative here would give me the slope of, say, a tangent line. So you give me, for a given x value, this will give me the slope of it. This is explicit. Well, what about implicit then? Implicit, and we'll go to black here. This, let me give you a familiar, what if I had something you're familiar with? I give you one of a familiar conic section here. You might recognize that as a circle. Okay, let me draw that. It's a circle of what? Radius 5. See how good I am at drawing a circle. Oops, didn't connect that very good. It's kind of like how I putt. This is 5, 0, right? This is 0, 5. And here we got a circle. Notice we still could be interested, and we still are interested in knowing, at this point here, what is this tangent? What is the slope of that tangent line? Or maybe over here, what is the slope of that tangent line? So we're going to be asking you questions to find what's dy dx. Now in this case, you see, this isn't even a function of x. It's a relation. It's a relation. For one value of x, I got two values of y here. Got one here and one here. So in this case, what I like to say is y here could be maybe an implied function of x, and I might write it like that. I might say y, the variable y here, it is a function of f. If you give me an x, I can give you two y's that satisfy it. And I might rewrite this as the following. I'd say x squared plus y. And I'll just put, they don't write this in textbooks, but remember, y is a function of x, and I'm going to write it like this, squared. Okay? And now the question here, the question is going to ask you, well, what's dy dx? Okay, so when we start this, just as we did up here, we took the derivative of both sides, right? The derivative of the left side was just y primed, or maybe I'd write it like this, dy dx. Remember notation. So the left side of this was dy dx. The right side was just 2x plus the cosine of x. We'll do the same thing here. Let's take the derivative. We're working on this equation now. Let me change it up. We'll go to green. The derivative of 2x then is just, the derivative of x squared is 2x plus, and let's leave this one. Let's just write this down. I want to know the derivative of y with respect to x. Y, function of x squared. dx. I'm not going to do this yet because that's what I want to focus on. The derivative of 25, what's the derivative of a constant? That's just 0. Okay, so let's focus in then on this thing, this term right here. And you notice this is why we study implicit differentiation after a chain rule example, right? So if I, just to make this look a little, let me give you a chain rule. What if I said the derivative, and you might have seen something like this, of f of x squared dx. You'd say that's equal to what? You'd say, well, that's 2. The derivative of the outside function is x squared. So I'd say that's 2 times f of x to the first power. Then I got to multiply that by the derivative of the inside, right? The derivative of the inside is just going to be, let's call it f prime of x. Okay? That's the chain rule. You could put the f of x here and the 2 over here. But here's the chain rule on this function of x. The same thing's going to happen to this. Well, this is just another way of writing a function of x. So what's the chain rule going to give me here? This is going to be 2y. I'll write it y. I'll still leave that x in there, but I'm going to drop it pretty soon. Y to, this is to the first power, by the way. That's not prime, so I really could erase that. You know, I could just, and I'm not going to write first power. Times what? What's the derivative of the inside here? Well, what kind of notation do we want to use? How about if we use y primed equals 0? Okay, well, let's put this all together, and we get what? We get 2x, bringing that down, simplifying this, plus 2. I'm going to get rid of the y of x. I'm just going to say y. Now, remember, y is an implied. It's implied that that is a function of x times y primed equals 0. Okay, well, that's all well and good, but what am I trying to do? What am I trying to find? I'm trying to find dy dx, or, you know, I'm writing this as y primed, right? Same thing, different notation. So now I want to solve for y primed. I want to solve for that. So I do a little algebra, and let's see here. I will go 2. I'm going back up here now. 2y y primed is equal to, that's a prime now, is equal to minus 2x. I want to solve for y prime. I say, well, y primed is equal to minus 2x over 2y, or that's just equal to minus x over y. Okay, I've redrawn things here just to give you kind of the result we just found. We've got this equation of a circle, or an implied function of x. Not really a function, as I talked about, a relation, right? We got a circle here. But we found that dy dx, when we took the derivative of y with respect to x, we got this relationship, minus x over y. So notice, the derivative is now a function of x and y. This is only good, this equation determining the derivative is only good for xy pairs that are up on this curve, okay? So let's look at this, see if it makes any sense here. So I'm going to plug in, how about this, at this point here, well, let's take a 0, 5. X is equal to 0, y is equal to 5. I'm here. This would say at this point, let's just write it this way, dy dx at x equal to 0 and 5 is going to be what? Well, it's going to be minus 0 over 5. It's going to be equal to 0. Oh, hey, that makes sense too. Look, which is good. It's always good when the math matches, right? You would expect a horizontal tangent line at that point. Let's try another. So this is like what I introduce a horizontal tangent line. Horizontal. In trouble with that. Horizontal tangent. Let's just. Let's try this point here. Let's try this point here. Maybe we'll mix it up and go to red. How about 5, 0? Well, in this case, dy dx at 5, 0 is what? Well, it's equal to 5 minus 5 over 0. Ooh, that's undefined. Undefined or infinite, right? Undefined. Let's just say undefined. How about not defined? And does that make sense? Well, sure it does. It makes sense because, look, we've got a vertical. This is one of these cases where the derivative does not exist. We got a vertical tangent line. Well, how about we pick a point, see if this equation still makes sense. Let's look at another point over here. How about the point right here? And we got a 3. Let's say this is minus 3, minus 4. Minus 3, minus 4. Okay, that point right there. That's on. Notice this is on a circle. If you put in 3 squared plus 4 squared, you're going to get 5 squared, which is that. So this point is on this circle. What's dy dx? Well, dy dx is going to be minus 3 over minus 4, and that's just going to be minus 3/4. And that kind of looks good, doesn't it? Yeah, that's negative. Certainly a negative slope. Okay, so notice what this gives us. Only for points x and y on this curve, this gives us the slope of the tangent line. We can use this relationship. The questions might ask you, well, where are you going to find horizontal tangents? Well, when is this equal to 0? dy dx is equal to 0 when the numerator is equal to 0. So when x is equal to 0 here and here, you've got horizontal tangents. How about vertical tangents? Vertical tangents are when the denominator are going to be equal to 0. Where are those? Well, those are here. So it kind of tells us a little bit of this relation, gives us some qualities of this relationship between x and y. Remember, this isn't a function. This is a relation now. And again, I just want to remind you, though, this equation is not good. I can't put in like, well, x equal to 10, y equal to 0, or y equal to 2. Okay, this point, not on curve, not on circle. So I can't find dy dx if it's not on the circle. But for points on the circle, this equation gives me the tangent lines. And I could calculate a tangent line anywhere on that circle. Okay, see you soon. Bye-bye.